prematurely when with the small trees of a certain size. In our case, it's going to be logarithmic in the size of the original tree. And so the basic idea here at a high level. So those centroids that we have so far, they're going to be special nodes. And they're all together, they're all very well connected. So they're all connected with each other. And the other small parts that are remaining, we used our basic procedure on them, and they're sort of connected. Those special nodes are served as a beltway between those little small trees. And so if you want to go from one part in the graph to a different part, you use those special nodes as a beltway. You first find a centroid of your small tree, and then from your special node, go to a special node of the target tree and find your way to the target node. So they kind of provide a fast connection to the part of the tree that you're interested in. And using these techniques allow us to both have a better key derivation time and reduce the number of edges that we add to the graph. And as I said, this is not going to be necessary for every particular graph, but in cases when you want to make sure that the key derivation time is fast, you apply these techniques. And this is all I wanted to say about efficiency improvements, and now I'll talk for 2 minutes about extensions that we have to this work. As I said before, we have a security proof of the main scheme, but it's not the strongest security model possible. And yes, I said it works against an active adversary who can corrupt as many nodes in the graph as necessary, but that adversary will be able to distinguish a key from a random number. For example, if I see my parent's key, then if I combine that with the public information that is available out there, that I'll be able to tell whether it's a real key or not, and this is not desirable in many cases. And so instead, we can achieve security. We can show that the scheme is secure under key indistinguishability if we just modified it slightly. And so the key idea here is, instead of using the same key in the public information in encryption, we separate them. We split this key into two different parts, and one is going to be available as the public information, and other will be used for encryption. I still get just one single key, but I'll be able to generate both encryption key and key used in the public information. But to other people, those two keys look completely random. They're not related in any way if they don't know where it came from. So this is one extension. Another extension deals with efficiency improvements. And as I said earlier, those techniques that we had work only for trees. They're not just for trees, but for hierarchies of similar structure. The property that they need to have is that they can be recursively decomposed in smaller parts. And there are some other graphs that have the same property, but not a lot of them. And of course, we want this to work for general structure for general access graph. And it turns out that if we use the notion of the dimension of a graph and combine with this technique as a building block, you actually will be able to achieve much faster key derivation time compared to the original scheme. And this is all I had for this topic, and just want to conclude. I want to summarize the properties of the scheme and just briefly mention future directions. And so, as I said, we have a scheme for key assignment which has just one key per user class, and then allows the user to derive access to all objects below in the hierarchy using fast hash-based key derivation. And the schemas are resilient against collusions, as provably secure. All updates to the hierarchy are local, are handled locally. They do not affect any other part of the graph, and the key derivation is bound by the depth of the graph, but can be significantly improved if you use efficiency improvements techniques. And one of the future directions that someone might consider is temporal constraints, and or so-called time-based access control. And it's important in many cases, especially in RBAC models, when you have someone who is entitled to have access to certain things during their work business hours, but after a certain hour, they shouldn't have access to those things anymore. Or people who work in shifts, or even subscriptions. For example, like if I have subscription to access something on weekends or evenings, there are still all of them are going to be based on the time of access. And the last thing is support for collusion resilience and limited depth permission inheritance that we didn't achieve in the current scheme. And this is all I wanted to say today, and if you have any questions or any comments, I'll be happy to answer.
Is the last point there, does that handle a case where you have, you had one graph where the bottom node was connected to two higher nodes? Does this handle that case where you have limited permission inheritance, and maybe you have two nodes on the path on one side and only one node, so the level is different depending on which path you take? Yeah.
So you first, to be able to support this, you first want to make sure that it's layered. So if the number of nodes on one side is larger than the number of nodes on a different side, you just insert a fake node to make sure that the level stays the same.
So if you're on the key assignments running downward and upward, then is every node going to have access to every other node, or only to their own parents, only to their own ancestors?
No, it's going to be only to their own parents or ancestors. And as I said, the set of objects can be disjoint, right? So things that you can access going down may be different from the things that someone can access going up. But it's still, yes, I will be able to have access only to my parent and their ancestors if I'm going up. If I'm going down, they're going to be just my descendants. Do you have a question?
It's listed like future directions, but like for the temporal constraints, do you think you can achieve something without re-encrypting every time? And also, how do you, I don't know how much you've been there, but like, do you think there's a way to prevent if someone archives the data to use that archive later?
I don't think you can avoid re-encrypting. With this model in place, if you change the key, everything is already there. Everything is stored, encrypted, and then you'll have to encrypt everything with a new key. Yeah, this is. With this particular model, you probably don't want to have really fine granularity because you have to, encrypt your database, everything, and this particular work is concerned just with having, proper access. So if someone stores, if someone stores the content of a file, we can't do anything about it, and it's the case in many other models. But the key thing here is that it's much more easier to store just the key than to store a huge